In the previous video, we developed this circuit for adding and subtracting numbers. And I want to be able to test this. Now I can test this in KiCad, but to be honest, I haven't learned how to do that yet. So I'm going to stick to what I know and write a Verilog module. Verilog is a hardware definition language, and I'm just using Visual Studio Code here, and I can run logical simulations of any digital circuit. Each component we call a module, and so I'm going to start by creating modules for each of the pieces of the circuit. If I jump inside of our adder as a starting point, we have these 7.4 series chips, so these 74LS283. So I'm going to start by modeling the inputs, outputs, and functionality of this chip. So we have a 4-bit A, 4-bit B, a carry in, 4-bit sum, and a carry out. So I'll call our module adder4 for a 4-bit module, and we'll define in here the inputs and the outputs. One thing that I need to change here is that A is meant to be 4 bits. In Verilog, the way we do that is by saying 4:1. This indicates the indices of A. So the first index will be 4, then 3, then 2, and finally 1 at our least significant bit. And if I refer to the 4-bit adder, the 74283, then we can see the logic that's being implemented. I could go ahead and implement this entire circuit exactly as they've shown in the datasheet. However, the point of this exercise isn't to map out all of the ands and ors and the logic in this way. I can do it much more simply. In fact, if I look back to the front page of this datasheet, we can see up here that it tells us the function that is being performed. And this is all we need to implement. In fact, it gets simpler than this because we can see that A1 and B1 are just our least significant bits being added. A2 and B2 are the 2's place of our binary number. A3 and B3 are the 4's place, and A4 and B4 are the 8's place. And then we're adding the carry in as an extra 1's place addition. The output is made up of the 4 bits and the carry out. Notice that the carry out is multiplied by 16. And that's because our carry out is essentially a 5th bit. 2 to the 5 is 16. We can achieve the same logic by using the plus operator. So we'll use an assign statement, and this just means that the equality, so I'm going to say sum, is equal to A plus B. And A plus B will be continuously assigned to S. We also need to, of course, add the carry in. And this isn't quite the full picture though, because it doesn't account for carry out. Remember, carry out was that 16's place. So carry out is the 5th bit. We can join bits together with the curly brace notation like this, and this is saying that carry out, which is 1 bit, combines with the 4 bits of S to make a 5-bit number. And then 4 bits of A plus 4 bits of B plus the 1 bit of C, and this is potentially going to result in a 5-bit number. And that's the full module. So I'll create a new module for a 32-bit adder, and I'll add 8 of these modules in. I'm going to use my adder4. I can do that using an include directive. And this will essentially add the entire content of that file into this line. It's the equivalent to copying and pasting, but it just keeps our system a little more modular. Note that here I've created A and I've given it 31 to 0. So that's 32 bits, and I've said that bit, the leftmost bit is bit 31 and the least significant bit on the right is bit 0. So I've created the adder32 to match our circuit. We've got A and B as 32-bit inputs, carry in as a 1-bit input, S as a 32-bit output, and C out as an output. And that matches the outputs that we defined down the left-hand side. Note that I can ignore VCC and ground. These are power signals, and I'm only interested in logic. So the Verilog code is only going to simulate the logic, and we can ignore those two. Next, we need to wire them all up. So I'll create 8 modules. We only need bits 3 to 0 for A in this module, and bits 3 to 0 for B. Notice here that A0 to 3 is our A input, B0 to 3 is our B input. On the next module, on U2, we'll have A4 to 7, B4 to 7, and each module is going to select the next 4 bits of A and B. Now we've got a problem here. We need to wire up all of these connections. So what I'm going to do, we've got 7 connections here, 1, 2, 3, 4, 5, 6, 7, between our modules. So I'm going to create a carry bus, if you like, and it's just going to be a wire, and that way I can use the various carry bits here for our out. So C1 is the carry out from module U1. So that's this carry here that's coming out of our U1. So this will be carry 1, and then this will be, then this one here will be carry 2 to match U2, and so on. So the input, the carry in for U2, will be C1 from Unit 1. So I'm just copying and pasting here. There is a better way of doing this, but for the sake of making this clear, I'm going to copy and paste 8 lots of these lines. We've got the carry out at the last module, but actually I've got the incorrect carries here. So this actually needs to be carry 7, 6, 5, 4, 3, 2, and 1. So carry in through to carry out. Carry 1 comes out of the first module and into the second. Carry 2 out of the second module and into the third, and so on. So this logic here replicates the carry connections that we have over here, and the outputs and the inputs are all selecting from our 32-bit I/O on the side here. So if we return up to our root level, we've implemented our adder. Now we'll implement the exclusive OR system. So we've got 32 bits of exclusive OR in here. Now, unlike the adder, there's no wiring inside of here. Our inputs go into a single gate, or in the case of the invert input, it goes to every gate, and then the output from the gate goes to the output of the circuit. So I'm going to wire this up in a slightly simpler way without having to create individual modules. I'm not going to create a 4 exclusive OR, a 4-bit exclusive OR. I'm just going to model it directly. So the logic is just an exclusive OR. So again, we can use an assign statement so that we are continuously setting the value of our output Y to be equal to A exclusive OR, which in Verilog is the hat symbol, and inv. Now this isn't quite right because inv is only 1 bit and our A input is 32. So if we come back to our circuit here, let's look at it at the root level. So our A here is 32 bits and our invert is 1 bit, and we want that invert there to be wired up to every one of our exclusive OR gates, and then A0, A1, A2, all the bits of A should then be wired up to the other input pin of our I/O. To do that, we need to extend this invert bit out to 32 of the same value. We can do that easily enough with the curly bracket notation like so. So this means that we have 32 lots of invert in a single 32-bit number. So now we have 32 bits for A, we have 32 bits that are all just the value of invert, and then the exclusive OR will do a bitwise operation on all of that. So that's our module. Stepping back out to the root, we now have both of these modules. We need to create our final add subtract module that puts these two together. Okay, so I've just set this up the same way that I've set all of the others up. I've copied, missed something there, need a B. So A and B as our 32-bit inputs are taken straight from A and B here. So they're our external AB inputs. And then we have a sub input that tells us whether or not we are subtracting. Our outputs are the result and the carry out, which is just C. So I now just need to create instances of our two modules. Now for our exclusive OR, the next value, if we go back to our exclusive OR module, our next value is the Y output. That corresponds to this connection. So the Y output from our exclusive OR is wired up to the B input of our adder. To do that, I'll create a wire that is 32 bits to match B and Y, and I'll call that Y, and we'll wire that out of our exclusive OR. I'll then create the adder and wire the Y in there. So now we have A and Y as our two inputs. Recall that adder 32 has A and B. So our A and B here are A and our Y output. And that is our full module. So again, these are very simple modules, and it's almost overkill to be testing them with Verilog. However, as the CPU grows, as I build the rest of the ALU and all of the other circuitry, it will be nice to know that what I have in hardware matches something that I can simulate in software in order to error check along the way. To test that everything's working as expected, I'll write a test case. The test will just be another module, but this time with no inputs or outputs. So I've created an instance of the add submodule here and wired it up to some registers, fix that typo, to some registers up here. This means that I'll be able to set A and B and whether or not I'm subtracting, and then observe the result. The initial block here will run when the simulation starts. Each scenario in this block will test a set of inputs. And after each input combination has been set up, we need a delay. So for the first test, I've just set A and B equal to 0, sub to 0, which means that we are adding, and then I have this #1 here. The #1 notation just means that there is going to be a delay of 1 time unit, in this case the default time unit of 1 nanoseconds, and that tells the simulator to propagate all changes through to the output. I can then display the output with the display command. The %Ds here are just placeholders. So these 4 placeholders that I have here correspond to these values here, A, B, result, and C. I'll throw in a few more scenarios and then we can test. Okay, so I've run the test, and our initial test case of 0 plus 0, we can see that the output is 0 and there is 0 carry. And I've just put in brackets over here the expected result in each case. So I can see that the expected result is lining up in every case. I've covered a few additions, a few subtractions, and down here I've covered maximum values. And they all seem to be working as expected. I'm pretty happy with that. It gives me confidence that I haven't made any major mistakes. But hardware definition languages like Verilog have one more trick up their sleeves. I've connected up the add sub module to the I/O on the Arctic 7 FPGA here. The board I've got here, the Basis 3, has 16 switches, and I've connected the left 8 of these to the A input and the right 8 to the B input. So we can test by adding some numbers. I've just got it set to add by default at the moment. So we've got 1 plus 1 is 2. If I put 7 in here, 7 plus 8, we've got 15. So it seems to be working in the basic case. Now I can also, if I just do 8 here, I can also switch all of these on. And I've sign extended the number here. That means that when I set this to a 1, it will extend all those ones out. So I'm actually dealing with a 32-bit number. So all 1s, you might recall from 2's complement, is actually -1. So I'm adding -1 to 8 here. If I set them all to -1, we get -1 plus -1. I've set the button in the middle here to change the mode to subtract. So if I press that, we get -1 minus -1 is 0. So this all seems to be working. I'm very happy with that. As I build the CPU, I'll keep adding to the FPGA code, and we'll be able to see the full RISC-V processor in operation before we print the PCBs. In the next video, I'll see if I can get the PCB design completed, ready for printing.